In this video, we're going to review some functions we should already know a little bit about from pre-calculus and trig courses. We're going to talk about the inverse trigonometric functions, exponential functions, and logarithmic functions. All of these functions come up in calculus quite a bit, so it's good to have a brief review of what they are so that we can handle them when they show up. So first, we'll start talking about some of the inverse trigonometric functions. Here's some definitions. The inverse sine function, which we write as either sine inverse x, where the inverse is indicated by that little -1 up top, or sometimes people use this notation, arc sine of x. This function is the inverse of the restricted sine function. Sine of x, where x is between -π/2 and π/2. So remember, inverse functions can only exist if you have a one-to-one function. That's a function that passes the horizontal line test. Our just generic sine function does not pass the horizontal line test. It keeps oscillating up and down forever. So we restrict the domain to be between -π/2 and π/2 and find just the inverse of that little piece. And that inverse is our inverse sine function. We have similar definitions for inverse cosine, inverse tangent, and so on. So let's get those definitions down. The inverse cosine function which is, again, either cosine with a little -1 of x, or arc cosine of x, is the inverse of the restricted cosine function. Cosine of x, where x is restricted to be just between 0 and pi. The inverse tangent function, same notation, tan with a little -1 and x, or arctan of x, is the inverse of the restricted tangent function, where we smush x between -π/2 and π/2, not including the endpoints. And then I'm just also going to quick define the inverse secant. So our inverse secant, or arc secant, is the inverse of our restricted secant function, where 0 less than or equal to x less than or equal to pi, and x not equal to π/2. Now, I am going to point out with this inverse secant function, there are a lot of different definitions out there. This is just one particular restricted secant function we can use to find the inverse secant. This one just happens to match up with a lot of our computer algebra systems, which is why we're choosing to use this definition here. So all of our inverse trig functions are continuous on their domains. So we should know what the domains are so we know where they're continuous. So let me write that down quick. All inverse trig functions are continuous on their domain. So let's just make a chart real quick of the 4 inverse trig functions that we talked about so far. We'll have our function, we'll have our domain, and our range. So my sine inverse has domain -1 to 1 inclusive, and range -π/2 to π/2. Inverse cosine also has domain -1 to 1, and it has range 0 to pi. Our inverse tangent has domain all real numbers and range -π/2 to π/2, not including the endpoints. And our inverse secant has domain -∞ to -1, union 1 to infinity, including the -1 and +1. And it has range 0 to π/2, union π/2 to pi, not including that π/2. So we're going to do an example where we try to find out where a function that involves inverse trig functions, where it is continuous. So where is this function, f of x equals secant inverse of x divided by pi plus 4 tangent inverse x? Where is that continuous? Well, we already know that the ratio of continuous functions is continuous, and we know that inverse trig functions are continuous on their domain. So I already know that the numerator is going to be continuous on its domain. So let me write that down. The numerator is continuous on its domain, which was -∞ to -1, union 1 to infinity. And my denominator, remember the domain of inverse tangent was all real numbers, so my domain for the denominator is everything. So it's continuous everywhere. But I do have to check one more thing. I can't just say that this entire function together is continuous on the domain of my numerator, because I have to make sure that I'm also not dividing by 0. So we need my denominator to not be 0. So to figure out when that's 0, set it equal to 0 and solve it for x. So let me solve that. We have pi plus 4 tangent inverse x equals 0. Well, that would give me tangent inverse x is equal to -π/4. And to figure out what x is, we just take a tangent of both sides. X is going to be tangent of -π/4. And tangent of -π/4 is -1. So this tells me x is -1. That is something that is not in the domain because it makes me divide by 0, and so I'm also not going to be continuous at x equals negative 1. So I already knew that this function was continuous on this interval here, negative infinity to negative 1, union 1 to infinity, but now I also know that I can't have negative 1. So that means that, put it all together, my function is continuous on negative infinity to negative 1, not including negative 1, union 1 to infinity. All we had to do was find where the numerator was continuous, where the denominator was continuous, and then make sure we're also not dividing by 0. So something else that we can do with our inverse trig functions is you can figure out a lot of cool identities with them by using a right triangle. Let me just do an example where we do some of that. We're going to use the triangle to find sine of cosine inverse of x. And here's our triangle. So I have x, 1, square root of 1 minus x squared. This angle down here is sine inverse x. And the angle up on top is cosine inverse of x. Remember that since our sine and cosine are regular trig functions, take an angle as the input and output's a value, our inverse trig functions, their output is actually the angle. So that's why these angles here are labeled with inverse trig functions. So we're going to use our right triangle and things you've probably learned in trig class, or maybe even back in high school geometry, to find sine of cosine inverse. So my cosine inverse x is this angle up here. I know the sine of that angle is going to be the opposite over the hypotenuse. So I have sine of cosine inverse x is the opposite of that angle over the hypotenuse. So I get square root of 1 minus x squared over 1, which is square root of 1 minus x squared. And let's just do a couple more using the same triangle just to get some more practice. So using the same triangle, let's find, how about cosine of cosine inverse of x. And I'm going to use the triangle to find this, even though I don't really have to use the triangle, but just to emphasize what we were doing. So cosine inverse x is this angle up here. To take the cosine of that, I need the adjacent over the hypotenuse. So that's x over 1, which is x. And this should not be a surprise because cosine and cosine inverse are inverse functions. They undo each other. So you can think of this cosine and that cosine inverse undoing each other. You just get the input of x back out. And just to do one more, let's do the tangent of sine inverse of x. So now we're talking about this angle down here, sine inverse of x. Tangent of that is going to be the opposite over the adjacent. So the side opposite of this angle is x, and the adjacent side is square root of 1 minus x squared. And so now I know that tangent of sine inverse of x is x over square root of 1 minus x squared. So that's just a very, very brief review of inverse trig functions. If you feel like you need a little more review, I would suggest to take a look in your textbook or Google some more inverse trig functions. I was just trying to do a very brief overview of them so we can move on and get back into our calculus a little bit more. So now we're going to move on to our brief review of exponential functions and logarithmic functions. So let's start with exponential functions. the exponential function with base b is f of x equals b to the x power, and we have b is bigger than 0 and b is not equal to 1. So an exponential function is one who has an input in the exponent. So I have a fixed base and it's to the x power. As you change your input value x, you're changing the exponent on this base. So the graph of an exponential function is going to look very, very similar no matter what the base is. So I have two possibilities for the graph. One possibility looks like this in green. Goes to the point 0, 1. This is b to the x if b is bigger than 1. And my other possibility is if b is some fraction between 0 and 1. And then it looks like this, just reflected across the y-axis. So this is b to the x when b is between 0 and 1. So no matter what the base is, it's going to go through that 0, 1 point, and it's going to have one of these two shapes. It might be a little bit skinnier or a little bit fatter, but it's that general shape. Notice it's always above the x-axis. That means it's always positive. And when we think about our limits that we've been talking so much about, I can see that if I have b bigger than 1, then the limit as my x goes to infinity is going to be infinity. And the limit as we approach negative infinity is going to be 0. And vice versa for having a base between 0 and 1. So my domain for exponential functions is all real numbers, but my range is just the positive real numbers. So the domain, negative infinity to positive infinity, range 0 to infinity, not including 0. And there's one very particular exponential function that we work a lot with. It's called the natural exponential function. And the natural exponential function is f of x equals e to the x, where e is our mathematical constant that's approximately 2.718. That is Euler's number. This number comes up quite a bit in higher mathematics. You're going to see it all the time in calculus. So we use this natural exponential function an awful lot. Now, we usually say e is about 2.718, but just for fun, because this is a calculus course, I'm going to show you different ways to define e using calculus. So here's some facts for us. The limit as x goes to infinity of 1 plus 1 over x to the x power is equal to e. The limit as x goes to negative infinity of that same function is also e, and also the limit as x goes to 0 of 1 plus x to the 1 over x power is also e. So those are three different ways to write down a definition for e using limits. We are not prepared to actually show why that's true yet, but later on, we'll be able to have enough skills to actually calculate those limits and show that it's equal to e. So stay tuned for that. So that's our exponential functions. Let me give us some definitions of logarithmic functions, and then we can finish up with some examples using both exponential and logarithmic functions. So the logarithmic function with base b is f of x equals log base b of x, which is the inverse of b to the x. So our logarithmic functions undo our exponential functions. They're inverses of each other. Since they are inverses, I know that the domain of my logarithmic functions is going to be 0 to infinity, and my range is going to be negative infinity to positive infinity, because inverse functions flip-flop their x and y's, so it's going to flip-flop the domain and range that we had earlier for our exponential functions. Let me draw the graph of these logarithmic functions. And just like with our exponential functions, we have two possibilities for what the graph looks like, but the point 1, 0 is going to be the important point this time, rather than the point 0, 1. So I have two possibilities. The first one I'm going to put in red, goes through this point at 0, 1, and just keeps going up forever. This is log base b of x, where b is bigger than 1. My other possibility looks very similar, it's just flip-flopped. This is log base b of x, where my b is between 0 and 1. So looking at the graph of our logarithms, we can see a little bit about our limits as well. I know that the limit as x approaches 0 of log base b of x when my b is bigger than 1 is going to be negative infinity. If my b is between 0 and 1, that limit's positive infinity. And we can see that the limits as I go to infinity, it's either going to be positive infinity or negative infinity, depending on what our base is. So just like we had a natural exponential function, we also have our natural logarithmic function. And that is the one that is used the most commonly in our calculus courses. So the natural logarithmic function has base e, that same e as earlier. And it's denoted by ln of x. So we use special notation for the natural logarithm. It's ln rather than an log. Now, when you see a logarithm, log base b of x equals y if and only if b to the y power equals x. That's the way you rewrite it in exponential form. So using the same logic, I know if natural log of x equals y, then e to the y is going to equal x. Let me write that one down. So natural log of x equals y if and only if e to the y power is equal to x. So now I'm going to write down a few properties of our logarithmic functions. Then we're going to do a couple of examples where we use the properties and also solve a couple different equations. Properties of logarithms. We have that log base b of a product a times c is equal to log base b of a plus log base b of c. So if you have a product inside of your logarithm, you can split it up as a sum of two logarithms. Our next property says if you have a quotient inside of your logarithm, you can split it as the difference of two logarithms. And our third property says that if you have a log of something to a power, then that power can come down in front of the log and multiply. So log base b of a to the n power is equal to n times log base b of a. So we're going to use these three properties here to expand a really complicated looking logarithm into a sum or difference of less complicated looking logarithms. Then we're going to expand the logarithm. Natural log of x squared times sine of x to the third, all divided by the square root of x squared plus 1. So the first thing I notice when I look at this logarithm is it's a natural log of a really ugly fraction. But the important part is it's a fraction. So I have a quotient here, and I can split it up as the difference of two logarithms. So the first thing I'm going to use is that second property that said I can have this rewritten as the natural log of the numerator minus the natural log of the denominator. And now this first logarithm over here has a product inside of it. So I can split this first logarithm into a sum. I'm going to have natural log of x squared plus natural log of sine x to the third power minus this natural log of square root of x squared plus 1. But I'm going to rewrite that square root as a 1/2 power just to make it more obvious why I'm going to do the next step. So now I don't have this written as simply as I possibly can yet, because I have all of these powers in here. So I can use that third property to bring the powers down in the front. When I do that, we get 2 natural log of x plus 3 natural log of sine x minus 1/2 natural log of x squared plus 1. And now that is as expanded as it can get. I have all the powers down in front, and I have no more quotients or products inside of my logarithm. So that is as expanded as that logarithm gets. Now we're going to do this whole procedure backwards on a different logarithm. So we're going to rewrite as a single logarithm. I have 1/2 log of x minus 3 log of sine of 2x. And I'm going to point out that this log that doesn't have a base written on it, and it's also not a natural log, that has base 10. So if you didn't remember that from a previous course, just a reminder that log with no base next to it is a base of 10. The first property I'm going to use to rewrite this as a single logarithm is I'm going to bring these numbers that are in the front up on the inside as exponents. So I'm going to get log of x to the 1/2 minus log of sine of 2x to the 3rd power. And now I have a difference of logarithms, so I can rewrite that as a log of a quotient. So I have the x to the 1/2 in the top, that's a square root of x. And in the bottom, I have sine of 2x to the 3rd power. And now I have just one single logarithm that's equivalent to the original expression. All right, now let's do a few examples where we actually solve things using exponential and logarithmic functions, just to get a little extra review. So solve for x. And my first problem is natural log of 4x minus 3 natural log of x squared equals natural log of 2. First thing I'm going to do is rewrite the left side of this equation so that it's written as just one logarithm. So I'm going to move this 3 up as an exponent. That will get me natural log of 4x minus natural log of x squared to the 3rd power, which is x to the 6th, equals natural log of 2. And now I can rewrite this left side as one logarithm with 4x on the top and x to the 6th on the bottom. Now inside this logarithm, I can simplify a little bit. We can cancel out one of those x's. So I'm going to get natural log of 4 over x to the 5th equals natural log of 2. And so now I have a natural log of 4 over x to the 5th equals natural log of 2. And that means that the insides of these two logarithms have to be equal. And this is now the equation I have to solve. We can solve that by multiplying by x to the 5th, dividing by 2, and then taking a 5th root. And I get that x is equal to the 5th root of 2. Let's do 2 more solving problems to wrap up this video. Let's solve for x in 3e to the negative 2x equals 5. So the first thing I'm going to do is try to get the exponential by itself. So I'm going to divide both sides by 3. And now I have to remember how to undo an exponential. To do that, you're going to want to take a logarithm. Remember, exponentials and logarithms undo each other. And since I have a natural exponential function, I'm going to want to use a natural logarithm. So if I take a natural log of both sides, my natural log of e to the negative 2x would just get me negative 2x, because natural logs and exponentials undo each other. And on the right side, I have natural log of 5/3. Then to figure out what x is, we just have to divide by negative 2. And I get x equals negative 1/2 natural log of 5/3. And just one last problem. We have e to the x minus 2x e to the x equals 0. And we're trying to solve for x. So when I see this, my first instinct is to factor out that e to the x. So I get e to the x times 1 minus 2x equals 0. And we know when we have two things multiplying together equaling 0, either the first piece is 0 or the second piece is 0. Now this first piece, we know that e to the x is never going to be 0. Remember, our range for e to the x was 0 to infinity, but not including 0. This is no solution. And for this one, I just add 2x to the other side and divide by 2. And I get my one answer of x equals 1/2. That's the solution to this problem. So that was just a very brief review of some of the things you've probably learned in pre-calc or in a trig class before. Our next video, we're moving back into calculus. We get to start with the definition of a derivative. And calculus is all about limits, derivatives, and integrals. So we already know limits. Next is derivatives. I will see you in the next video. If you have questions, you can ask them below, or you can email me or come to office hours if you're one of my current students. I will see you next time.